In this lesson, we're going to talk about the physics concept of power. So, to begin thinking about this concept, let's think about if your phone at the end of the day is down to a charge of 20%. You plug it in, and overnight it charges up to 100%. So, if you used one charger versus another, a slow charger versus a fast charger, how would that compare in terms of the amount of work that is done on your phone to charge it? Please take a moment to think and come back to us. You can pause and come back once you've kind of thought this through. So hopefully as you thought it through, you considered that, well, work is the change in energy. So if we're going from 20% charge on our phone to 100% energy in the battery of our phone, then we're going some amount of energy, right? And no matter whether we use a fast or a slow charger, or no matter the speed of that charge, the same amount of work should be done, right? However, it can be done quicker or less quickly, quicker or slower, right? And that is the idea of power. So in physics, power is the rate at which work is being performed. And that means that the more rapidly a force is exerted, the more power has been exerted. And we can mathematize this formally with an equation. We'd say that P, or power, equals W, or work, done over time, divided by T for time, right? And really what this finds us is the average amount of power exerted over that whole activity, right? Because really our work is our change in energy from the initial state of our system to the final state of our system. And again, we're dividing that over time to get our rate at which the work is being done. So can you take a moment to consider what base units, meaning kilograms, meters, seconds, power should be measured in if we're using the metric system? Pause, think for a moment. When you come back, first of all, the unit that we will use in the metric system for power is watts. So we have a new unit, but packaged inside of watts, we can break it down into our base units, the kilograms, meters, and seconds, right? And so if we think about our work or our change in energy over time, both work and change in energy are measured in joules. So we're taking joules divided by time, which is measured in seconds, right? So joules over seconds. If we break open joules, we'll find a couple things inside. One is we break it down into newtons times meters, right? Because really work is force times distance, divided by seconds again. And if we break down newtons, we can see that inside newtons is kilograms meters per second squared, right? Mass times acceleration. So overall, we end up with kilograms meters per second squared times meters in the numerator divided by seconds in the denominator. Or if we simplify, so we only have one fraction here, then in the numerator we end up with kilograms meters squared, and in the denominator we end up with seconds cubed. And again, we take those, and since we come across power often enough in physics, we decide, you know what, all these base units we'll package them up into a new unit. We call that new unit the watt, or W is what stands for watts, for a unit of watts. So we can calculate power for any activity. So let's take a look at Sarah here. Sarah is climbing the stairs. She starts at the bottom with a speed of 0 meters per second, and then she rises 15 meters to go the height of the stairs. By the time she gets to the top, she's moving at 2.5 meters per second. So if she weighs 62.5 kilograms, has a mass of 62.5 kilograms, and it takes her 16 seconds to ascend the stairs, can you find, using our equation of power equals work divided by time, how much power on average she exerted during this activity? Take a moment, and when you come back, the answer should be 587 watts. So obviously there are many other units we can measure power in the imperial system, or with automobiles and many vehicles. We often measure power in horsepowers. And unsurprisingly, horsepower is how much power is being exerted relative to the power of a horse. So this was created back during the transition of carriages into automobiles as our main forms of transportation, right? Where you could measure an automobile's power output relative to how many horses on a carriage would give us that same power output. So 1 horse equals 1 horsepower, 2 horses, 2 horsepower, 4 horses, 4 horsepower, so on and so forth, right? So we can think in the imperial system of measurement what this equates to, which is this is moving, 1 horsepower is moving 550 pounds 1 foot every second. So if you exert that amount of force over that amount of distance, by over this amount of time, 1 second, then you get a horsepower. And of course, we can convert that back into our metric system of units, which is 1 horsepower equal to 746 watts. So if we think back to Sarah going up the stairs from our example problem, we could take her power, her average power, which is about 587 watts, and we can convert that into horsepower by dividing by 746 watts per for every 1 horsepower, and we end up with her power output would be about 0.787, or about 3/4 of a horsepower. For a building, we calculate the amount of energy usage for a dwelling or a business in terms of kilowatt hours. Can you take a moment to think about how that makes any sense relative to the equation we were just talking about? And if you think a little bit, if we recognize that our average power output equals work or change in energy divided by time, if we reconfigure that equation to solve for a change in energy, then our change in energy, or the amount of energy used over a period of time, would equal our average power times the amount of time of the interval of activity we're looking at. So if we measure our energy usage in kilowatt hours, that makes sense because our average power would be in watts, or if it's large enough, kilowatts. And then our time we can measure in any unit of time, right? Which again, if it's large enough, we can measure in hours. So our average power times time, kilowatts times hours, gets us kilowatt hours, is another way to measure energy or to communicate the amount of energy that is changed in a system. So here is from my electric bill from 2023, and you can see that we use 430 kilowatt hours during this period of time this month. So knowing there's 430 kilowatt hours per month, and knowing that I'm not usually home, usually just the cat's at home, we can figure out how much power the cats used on average at my house during that month. So please try to figure that out and recognize, again, that our change in energy, which is a 430 kilowatt hours, should equal our average power times time. So just think about what unit of time we're thinking about and over what period of time. And you should end up with an average power that the kitties use of 639 watts. So we can think about how power relates to force and velocity, and we will find that it is the dot product of force and velocity. So can you try, based on our base equation here, that power equals work divided by time, can you try to derive an equation that relates power to force and velocity? Take a moment, maybe pause if you like. And once you come back, we find that work we can break down into our force times the distance that the object or system was moved while that force was acting on it, times cosine of theta, or cosine of the angle between the force and the distance vectors, divided by time, of course, because we're looking at power. So if we pull out our force and our cosine theta away from distance over time, we end up with force times cosine theta times our distance over time. And of course, distance over time is velocity. So this gets us our dot product of force and velocity, which again, if we multiply two scalars together, we have to account for the fact that they are not necessarily pointed in the same direction. And if we take the cosine of the angle between those two vectors, we do what in math is called the dot product operation on those two vectors, right? So we end up with, when we take the dot product or the cosine of the angle between those two vectors, we end up with a scalar quantity, which is why power, like work and energy, is a scalar quantity rather than another vector. And this gives us a way to determine the amount of power being exerted at any instant. So if we know the force, the velocity, and the angle between those two vectors, then we can figure out our power at that instant in time. And by knowing our velocity, we can figure out that power for that instant in time. Or what we might abbreviate as P, and then with a little subscript of instantaneous. And so we come up with this equation. We can formalize it with P instantaneous, or instantaneous power, equals our force, the amount of force that's parallel to our velocity, or our force times velocity times cosine theta. Again, that dot product of force and velocity. And finally, we can put this into practice with a practice problem. So if we take a look at Sisyphus here, pushing a boulder up a hill. So he's pushing a 172 kilogram boulder up a hill that has a grueling 42.0 degree incline. How much power must he exert if he is to push the boulder with a constant speed of 0.5 meters per second? So using our equations we derived today, can you please figure out the amount of power that Sisyphus needs to exert at every instant in time on average while he pushes his boulder up the hill? So that's all for power. Thank you for learning with me today.